Okay. Good morning, everyone. You are welcome to this. Yeah.
Yes. What's better there?
Can you meet? Can you meet?
Can you mute yourselves, Dr. Ali? Okay, please. Can you mute yourself briefly?
It's done.
All right, sir. All right. Thank you, sir. Oh yeah, you can go on, Dr. Ali.
Yeah. Sorry about that. Good morning, everybody. Again, you are welcome to this second series in a seminar organized by the Carnegie African Diaspora Fellowship Program and supported by 3 universities: Obafemi Awolowo University, Ile-Ife, Elizade University, Ilaramokin, and at the College of New Jersey here at the United States, and powered by 3 of us who will be presenting today. Kola Ogumba of OAU, Rasak Alioke of Elizade, and Ambrose Adegbege of TCNJ. I'm going to hand over right now to Kola Ogumba to start the proceeding. Thank you.
Okay, thank you very much, Dr. Adegbege. I will kick off the discussions today by talking about one of the core objectives of the program, which we have embarked on, which is curriculum development. And so I will share my slides shortly. It's such an important part of the whole program because obviously the whole idea is to increase the quality of transmission of knowledge. And of course, up-to-date curriculum is a very central part of that objective. And so in about 10 minutes or so, I will quickly run through some of the efforts that we have made to make this a reality. Just hold on. Okay. I don't know if you can see my screen well, but I assume you can. Now,
yes, we can.
Okay, this is the second in the series of our seminar presentations. In the first part, we talked generally about what the Carnegie African Diaspora Fellowship Program is about, how it came about, how it has been empowering scholars both in the West and in Africa. Now, today we want to go into the specifics of what we have done, and we're starting with curriculum development. And that's the topic of today, curriculum development specifically in embedded control. In the last presentation, there was an explanation about what embedded control is. For those who are not in the engineering field, it is a very simple concept. Essentially, there are concepts in control engineering which we use to control different physical systems, but we want to demonstrate it more when it comes to laboratory scale experiments, when it comes to things that we can show our students with the hope that they can take these ideas and then go on and build all kinds of solutions to man's problems. And so I have tried to build up to the curriculum that we have developed by talking about some level of background to the whole notion of developing curriculum. It's not just an exercise, it's something that is geared toward being impactful in how we train our students. We cannot train a new person on old material is not likely to make much progress. And the idea behind the evolution of man, and that's what I have referenced in this particular slide, is that we continue to improve. What we taught 5 years, 10 years ago may no longer have the same effect now as it did then. And so it's our responsibility to move with the times and to ensure that what we're delivering to our students is still very much relevant to the addressing of the problems of the world. And so curriculum development is important. That's why there are accreditation exercises in different universities. That's why we're doing what we're doing. And embedded control specifically has emerged as a very important part of recent life, because of course we are all aware of the proliferation of computers. Every phone, every laptop, every device these days has some computing going on in it. And so, and computational power has become very considerable compared to the 50s and 60s. Now we can compute so much just with our phones. Our phones are incredible devices in terms of computation. So computational power has become available. Why don't we use it? And one of the ways of using it is to build specialized systems, microcontrollers, microcomputers, specialized computers, all kinds of things that can address specific problems that exist within particular places. And so it's useful to have a course, more specifically now in control engineering. And control engineering has had a reputation of being abstract, being very difficult to understand, being irrelevant as far as we are concerned to daily life. But now we are saying that's not true. And one of the ways to demonstrate that there's a lot that can happen in control engineering is to bring theoretical concepts to life. And that will happen by not just teaching the ideas behind control, but to now show you how to put those ideas on chips, on computers, and then make them to control physical systems, not just simulations, not just something in space, something you can actually see and appreciate. And that's the whole idea of embedded control. So I've said here that there is a shortage of physical infrastructure that deals specifically with control engineering in our schools, shortage of manpower and so on. There are many challenges we face here, but this is the first step to reducing that problem. And we will show as this seminar goes on, and hopefully in the future, how this can happen. And it's not something in this, a pie in the sky, it's actually right here with us. Some of the equipment that we hope to use now and hopefully in the future are already with us. And people have been using them, as I've discovered, even beyond this program. So it makes sense to make us to know what is happening and to key into it. And then hopefully we can solve some of Nigeria's problems using some of the ideas we gain from these and many more interactions. So I've put as a final point here that students will be greatly inspired when the theoretical concepts that they have heard of or seen in books can actually be made to change temperature or change liquid level or change the illumination in a house or change the speed of movement of a car, change the or maintain the level of water in the radiator of a car. So many things we can do with control engineering, moving from abstraction to practicality. And so I've put here some of the intentions of our efforts to build a curriculum. What exactly do we want students to be able to do? We want our students to be able to build, or first of all, design hardware and software interfaces so that we can sense and we can control simple engineering systems. Now, there are so many things around us which we may not know are engineering systems that are control systems. One of them is the bathroom toilet tank. When you flush water in your house, what you're doing is injecting a disturbance into the level of water in your system. And the fact that water flows back, hoping that you live in the kind of society where water actually flows back, then what is actually happening there is a regulation situation. And it's a control problem. The same way when you have a water heater and you decide to do a mixing of water such that water arrives at a particular temperature that you want, what you're doing again is control. And we hope that with this course, we will open your eyes to so many possibilities as far as the infrastructure that a control system needs is concerned. And then we talk about designing and implementing control algorithms for real-time embedded systems. Now, for those who know control engineering well, there are many control ideas that exist, many of them in the abstract, many of them with things like transfer functions, like state space, all kinds of very elegant control ideas have already been created. But what most of our students do is just to do the math and pass exams and go home. But now we want to bring it to, the appliances around them. And the idea is that when we have taught you the concept, we will now teach you how to put that concept on a computer and how to make the computer run to do a specific physical task. Very important. And then we'll also talk about, one of the intentions also is to teach how to prototype functional systems. And then, of course, to understand that in reality, there is always a trade-off. You can't get all of what you want. And so you'll always have to trade something off for something else. It's a general life concept. It's also a very important concept in control engineering. So there are 4 core aspects of the curriculum, and I'll discuss them one by one and try to highlight the subcomponents of those functions. The introduction to embedded control, what exactly is it? And so there are 2 key subsections we've defined here. We will go through a whole lot of things that serve as platforms for us to build embedded systems. Key in this whole discussion would be what is called the microcontroller. And for those who have heard the name before, or those who have not, it is just a specialized computer that does specific functions. So you can program it to achieve particular things. So as you can program it to do anything, so can you program it to do control. And that's the point we're trying to make. So we'll talk about its features. We'll talk about its abilities, what it can interface with, what it can interact with, and so on. The second key subsection is the issue of sensors, actuators, and interface circuitry. Now, when you are controlling something, you have to sense what you are controlling. Like a simple illustration is when you send somebody on an errand. You can decide that that person will not give you any feedback, let me use that word. But then it is risky. What if the person goes out and never comes back? So a way of making sure the task has been done is to ask the person, have you done that task? Now, by asking a person, it can be likened to sensing something. You're trying to find information about whether a particular thing has been done. And sensors are so critical in control engineering. In fact, what we call feedback in control engineering is nothing but measurement that is obtained from sensors. In the same vein, actuators are extremely important. An actuator is the actualizer of a control system. Let's use a driving illustration. If I'm driving a car, I am the control person that is moving the car around. And because I am using my hands and my feet to move things so that the car can move, then in many respects, my feet can be the actuators of the movement of the car. But it is my brain, which is the controller, that tells the actuator, which is the hands and the feet, what to do so that the car can change location from point A to point B. So as you are sensing with your eyes, looking around to see how you're going, your brain is reacting to what your eyes are telling it, and the brain is now telling the hands what to do. A very simple illustration, but it captures in many respects what this whole effort is about. And so interfaces are always important because what comes out from one subsystem of a control system may not fit what should go into another system that follows it. And so you have to condition, you have to transform, you have to do a number of things. And again, all these have been put into consideration as the curriculum is being built. The second core section is the hardware for embedded control systems. And there are quite a few of them. I've talked about introduction to control hardware here. There are things that are called field programmable gate arrays. There are things called field programmable analog arrays. There are microcontrollers. There are a host of subsystems that help to perform the controlling of the system. The execution of the control law can be done using these control hardware. And then the conditioning of a signal. Maybe a particular signal gets actuated by a current, and what is coming out from what should actuate it is a voltage. Then there might be the need for a voltage to current converter of some sort. Just as there might be a need for filtering, there might be a need for amplification, and so on and so forth. So I've listed here sampling, quantization, analog to digital conversion, digital to analog conversion. Now, ADCs and DACs will always be important in control for obvious reasons. The computer is a digital device. The system being controlled has analog variables. Temperature is analog, but it has to find its way into a computer somehow. So there will be an analog to digital conversion. And then when this computer is telling the actuator what to do, the computer comes out with a digital output, but a pump, for instance, needs an analog input. So there has to be some digital to analog conversion and so on. And then data transfer and communication protocols are also very important. How do you move data within a control system? I've listed a few of them: serial, parallel, UART, SPI, I2C, and so on. All these also have featured in our considerations. Because of time, I will run through the remaining points. So control algorithms. This is the part that our students know very well, because this is what we teach in class. PID control, state space control, controllability, observability, and so on. But now the idea is to make these ideas to come to a physical situation. And then things like how to implement, how to prototype, also a very important consideration. So hardware in the loop experiments, rapid control prototyping, these are some of the paradigms in control. Integrated development environments, I'm sure a few of us have heard of IDEs before, and so on and so forth. Real-time workshop, state flow, and the likes. So in a few seconds, this is what we have tried to develop. It is still being refined, but the hope is that this particular curriculum, after refinement, will be deployed in our respective institutions. And as that happens, hopefully it will engender discussions about how to do great things. And because we are all linked now virtually in some form or the other, then we will continue to share ideas even across the Atlantic. And they will continue to get better and better even as we go on. So this is as much as I have to say now. I'll now hand over to the next speaker to go into more details. Thank you very much for your attention. Thank you.
Thank you, sir. Over to Dr. Aleoke for his presentation. Thank you.
Thank you very much for the presentation. Thank you very much for the presentation, Engineer Gumba. One of the things the last speaker spoke about is about the course learning outcomes. And one of the things the next speaker will be speaking about has to do with teacher-scholar model. The question now is that how do we synergize achievement of the course learning outcomes and having faculty scholarship? One of the approach is to have faculty staff engage in lab activities of active learning practices that will also allow faculty to engage in research. That will also allow faculty to engage in research. And one of the avenues of doing that includes the Anagram boards and the TCL lab package. The Anagram boards basically is a programming of an analog signal processor. And what that does is that you're able to program different kinds of analog functions or circuits in the same board and have it perform the function that it's supposed to perform. This guy is an hardware version of the circuit simulators that we're all familiar with, the PSpice and the rest. Is an hardware version. So you have different kinds of circuits, whether digital filters, whether signal conditioning circuits and all that. And you have a single board that can do all this at once, depending on what you want. The next speaker will be speaking more about Anagram boards, but what I'll be focusing on is on the TCL lab package. It's a very low-cost embedded system. It just costs about $35, and it consists of 2 heaters and 2 temperature sensors mounted on an Arduino board. And it can easily work with any software that can send and receive commands from the serial USB connection. That is the MATLAB, the Python, and the Octave. I'll just show you a video link, a presentation of how it's connected. It's just having, just a second. That's the TCL lab package. And what you have underneath is the Arduino board, on which you now have the plant itself, which is the transistor and the thermistor. The blue cable is what powers the Arduino board, and the white cable is what actually powers the transistor. I must include a caveat at this point. The manufacturer states that it's preferable you power the transistor, that is using the white cable, using a separate power source. But for the sake of demonstration, it has been powered by the same computer. Now, there are 3 things I'll be discussing regarding this TCL lab package. One of them has to do with interfacing of input and output devices. The other has to do with dynamic modeling. And the last thing is digital PID control. These 3 things are what can be taught and learned using this TCL lab package. I'll start off with the interfacing of input and output devices. What we have on the screen there is the hardware architecture of the TCL lab package. We have the sensors, we have the actuators, we have the controllers. The sensor is simply your temperature sensor is simply a thermistor, which senses the temperature of your actuators, which are the transistors here. And the controller, as you expect, is the Arduino microcontroller that you have on this board. And with this hardware architecture, you can do a lot of things that has to do with interfacing of input and output devices. The previous speaker spoke about that briefly. You can teach students about signal condition and conversion, analog to digital conversion or digital filters. You can have students implement different kinds of digital filters on the Arduino on the TCL lab package, and for them to observe the effect on the output, which is the temperature readings. They can have a lot of things to do regarding that. They can implement different kinds of filters, adding key filters, a lot of kinds of filters to let them understand the differences between all these filters. Another thing that this package will allow students to learn is the issue of communication protocols. Most students are very familiar with Arduino, but some of them do not really grasp fully how these devices communicate. They don't really grasp fully the communication protocols between the different components they are interfacing together. So this particular package will allow students to learn more about that. We have different kinds of communication protocols. We have the SPI, which is a serial standard. Then let's move on to the next one, which has to do with dynamical models. Another thing that students can learn using this package is the models, dynamical models. What are dynamical models? This is simply a mathematical representation that describes the behavior between the input and the output of your system. In this case, the input of the system is the input to your transistor, the input to your transistor, and the output in this case is your temperature reading. So we now need to get a kind of representation that describes the behavior between the input, the heat input, and the output, your temperature that is read at the output. There are 2 ways of doing this. We have the mechanistic models. Basically, these models are derived using your fundamental laws of physics. You apply your not necessarily physics, can be from other natural sciences, but typically it's usually from physics. For in this instance now, for the TCL lab package, now you can use the energy balance equation to arrive at a model, which you have in equation 1. Basically, you have the one from convention. You're accounting from convention, and also accounting for radiation. And this particular model, of course, can be linearized about the equilibrium point to obtain equation 2. That is also another model, but this time around, this is a linear model, unlike one, which is a non-linear model. Another way of getting your models are called the ones that you obtain using derived from data, and these ones are called empirical models. You excite the system using the input, and you read off the output. So using the input-output data, you can actually derive the model of the system. And a typical example in this case, your first order plus delay model. And actually, there are other kinds of models you can actually arrive at using your derived data. And one of the things that this lab package will allow students to learn, especially in regards to deriving models from data, is the use of data analysis. So you have the data, you have an input and output data. You can do data analysis with this kind of data and see how it actually relates to what we have on ground, and actually opens the door to actually a bigger course, which is called system identification, which is basically you are analyzing data, input-output data, to get the dynamic model of your system. Now, I will run the simulation. I will run the simulation that will allow us to get the different kinds of models that I described earlier on. So it's running now, it's run for about 2 minutes. But meanwhile, I will go over to, this is the plot we've obtained earlier of this particular TCL lab package. Obviously, the red line, the red plot there is one due to the actual measurement, the temperature sensor readings. Then the black line there is due to the nonlinear model that I showed you earlier on, one obtained from the energy balance equation. As you can see, the nonlinear model actually approximates the behavior of the input-output model. As you can see, it's very close to the red plot, especially for the low temperature span between like 30 degrees to like 40 degrees. But beyond that, it starts to deviate, just like the linear model too. So basically what we have in this plot is the models, the input-output behavior, using different kinds of modeling approaches, whether it's a linear model, the Jacobi linearized model, or the first order plus time delay model, or the nonlinear model. That's what we have here. You can see it's actually reproducing the same kind of plots here, but this will take a while. So I can just stop it at this point. As you can see, it's actually similar to the plot I showed you earlier on. So I'll stop it at that point and continue with the presentation. So what I showed you earlier on now as the actual measurement, which is obtained from the temperature sensor. We also have the nonlinear model, the Jacobi linearized model, the first order plus time delay model. And this actually serves as a teaching aid for data analysis because you have an input-output data, which you can use different kinds of data analysis approaches to allow the students to be exposed to different kinds of data analysis methods, and also expose the students to the system identification methods, which is actually a crucial aspect if you are dealing with embedded control. And that's the plot once again. Now we move over to the last aspect, which is temperature control using digital PID. Ideally, we want to control a system. The system in this case is a combination of your transistor, which is being heated, and the temperature that is being sent. That's your system, that's your plant in this case. If you want to control a system, the first thing you need to do is to actually get the model of the system. That's what we did in the earlier slides. We obtained the model of the system. After obtaining the model of the system, you can now design your controller. I'll be using PID as a case study in this particular presentation. The first equation here is a typical PID controller equation, which is in continuous state. But of course, if you want to actually implement this, you have to implement it in discrete domain. And the discretization is what we have here. So we now implement this PID controller inside the Arduino. We can use, this is an example of a PID control algorithm. As you can see, the function that is here, we have our KP, our tau I, our tau D, which are the parameters for the PID controller. We have our KPK and KD. Then with these parameters, we can do your PID control here and get the output, which is our OP. Is this OP signal that is sent to the system, to the plant rather, which is the transistor. Is the value of this OP signal that is sent to the transistor. So now is the value of this OP that I showed you in the previous slide that is sent to the transistor, which is the actuator in this case, and it heats up the transistor. So once this transistor is heated up, the sensor, which is the thermistor in this case, senses the temperature readings of this transistor and is fed back. The difference between the set point and the measured signal is the error that needs to be eliminated by this PID controller. Now we'll now simulate this in real life using the TCL Lab package. But for the PID, this is a simulation of the PID. Now it has started. It will take a while, but before it finishes, I'll continue with my presentation. So I'll go back to my slides. So with this package, you can use it as a teaching aid for control theory. It's not only as a teaching aid for control theory, as I mentioned earlier, you can use it as a teaching aid for data analysis and system identification. As I also mentioned earlier, you can also use it as a teaching aid for interfacing, making students understand the communication protocol that is involved in an embedded system. That's communication. You can also use it to teach data analysis. Now, finally, you can also actually use it to teach control theory itself. One thing you will notice, this is the completed simulation. One thing you will notice is that there's a significant overshoot at this point here. The set point is at 40 degrees. After some time, set point is changed to 30 degrees. And the red one is actually the measured signal. One thing you notice there is that there's a significant overshoot here. And you can actually adduce this to the interaction of delay and saturation. Because as you expect, once you heat up the transistor, there's usually a delay before the effect can be felt by the temperature sensor. So by the time you actually, even if you send the right control signal, before you can actually sense the correct signal, the correct temperature at the output, there's a delay. And what the effect of that is that you keep increasing the control efforts you are applying, not knowing that it has actually been affected. So this will actually lead to saturation itself. And more saturation also leads to having more delay. So to get to the time in which hopefully the delay will have reduced to a reasonable extent that the saturation will no longer be will no longer have an effect on the system. And that's what's causing this increased overshoot at this point. So, and of course, it goes to steady state. So there's a kind of oscillation at this point, because you have to allow it to go, you have to allow some more time for it to actually reach perfect steady state. So, so definitely the students can learn a lot, especially in regards to control theory using this platform. However, that same platform can be used to test research ideas regarding anti-wind-up design. Remember in the last presentation, we talked about research work that has to do with anti-wind-up design. This is a perfect system that has wind-up effects, as I explained, that is leading to large overshoots. So you can use this platform not only to teach students, but also as a platform to experiment with your research ideas. You can use it as a platform for faculty or staff to test their research ideas, for example, in this case, on anti-wind-up design. And that actually ties into the concept my next speaker will be speaking on, which is this teacher-scholar model. So let me just have a look at what the simulation is doing. So let me have a quick stop at this point. So that's our simulation, the real-life simulation, or real-time simulation. It's not a real-time simulation actually, but it's not in real time. So that's the simulation that we just performed at this very minute now. As you can see, that is significant overshoot I talked earlier. So if you allow this to actually go to, if you allow some more time, this response will actually go to steady state. And that's the complete plot that we have here. In conclusion, what I've demonstrated so far is the use of the TCL Lab package as a teaching aid for embedded control system and as a learning opportunity for students that's going to be taking that course. It also doubles as an experimental platform that can be used by faculty staff for the purpose of their research. I will now hand over to Professor Adegbege to conclude the seminar. Thank you.
Thank you very much for a great presentation, Dr. Alioke. Now to Dr. Adegbege.
Okay, thank you very much. Let me share my slides. Okay, good morning. Thank you again for coming. And the idea is to present, to see the connection, teaching and using resources to be able to enhance student learning. And now what I want to talk about is how do we incorporate research? How can we get, our students to get involved in research? And hopefully my presentation will kind of connect the curriculum, the teaching aid, and the research possibilities that we have. I titled my presentation, Innovative Pedagogy for Embedded Control. And I'll kind of talk about three different topics. Number one, I'll kind of summarize what is a teacher-scholar model again? What is it all about? And then I talked about some innovative pedagogy, some active learning techniques that we hope to employ when we deploy the curriculum that our first speaker already expatiated upon. And then finally, I want to talk about the linkages. How do we link scholarship and the innovative pedagogy? How do we bring everything together within the embedded control course that we have developed? Okay, teacher-scholar model. From the last presentation we had, we said that teacher-scholar model is integration of scholarship and teaching within the same framework. That we know that scholarship involves discovery of or synthesis of new ideas or new knowledge, and the application of such knowledge to solve human problems, And teaching is a conveying, is a transmission, is a communication of those ideas, to people, to students in this context. And what you want to do is for them to be able to, excuse me, it's like there's fire alarm test going on.
Oh,
can you see hear me?
Yeah, we can hear you.
Okay, yeah.
You need to exit the building. You need to exit the building.
I think they've stopped it now. Okay, maybe there's a test going on. Okay, I'll
maybe,
continue.
Maybe false alarm. Yeah, thank you. Yeah.
Thank you. Now, therefore, we have teaching. Teaching involves communication of this new knowledge and the creation of capacity for inquiry and innovation. Now, teacher-scholar model is the amalgamation, is integration of these two techniques within the same context. Okay, therefore, based on the Carnegie Center Foundation for Advancement of Teaching, they have classification of scholarship, and they have 4 main categories of scholarship. Number one, your scholarship could be scholarship of discovery. This is what we are used to. This is a fundamental research that everybody refers to, that when you are doing research, it's original research that advances the state of the art. Okay. Now, the second class is the scholarship of integration. The scholarship of integration is synthesizing information across discipline. And you will see that in our embedded system course, what we have done is to synthesize information from optimization, from control theory, from circuit, from embedded system, and we bring everything together within. That is scholarship of integration, synthesizing idea from different cross disciplines, cross different fields. Then we have scholarship of application. This is actually using research responsibly to solve human problems, to solve consequential problems. And one of the aim of this course and the fellowship that we have done is to be able to see how can we solve our local problems, how can we solve Nigerian problem? In this case, in the context of engineering, how can control be used? And part of that is also training people, to train critical mass to be able to go solve this problem. Like I have had experience from the industry. Most of the problem we solved in the industry were outsourced. We were just hand carry, we just pass papers, which is really very, very disturbing. Most of the innovations and technology that are currently used, even in Nigeria, are all externally developed, though there have been a lot of progress made recent time in terms of all this technology paying system in the economy, which is really good. Now, finally, is the scholarship of teaching. This is systematic study of teaching and learning processes in a form that can be evaluated by peers. This is, and we hope to do that within the embedded control course that we have developed, so that we can use some innovative teaching techniques, okay? And then document it, collect data, and then share with our peers, that this is a way to go. Okay. That is the second part of my talk is about the innovative pedagogy for embedded control. And what I want to talk briefly about is these passive and active learning techniques. Passive and active learning are different methodologies for acquiring knowledge in the learning process. We are very all familiar with the passive style of learning. This is where you go to class. You just sit in there and the professor comes to class and just deliver. Sometimes the professor comes to class, he doesn't say anything. He goes to the board, writes for 1 hour, 20 minutes. I just say, see you later. Some professor will just say, okay, in the first class, I say, this is a curriculum. I see you in the exam. Go to the library, go and figure it out yourself. This is the passive teaching or learning technique, where the emphasis is on the professor. The emphasis is not on the student. Nobody cares about the student. The student has to go figure things out themselves. It is mainly teacher focused. But the active learning model, is kind of hold students responsible for their own learning. It involves students in the learning process, right? Students are the center. The methodologies are student-centered. And students learn by doing something and also reflecting on their experiences. And I'm going to give some examples. These are some of the practices in active learning methodologies. Number one, learning by doing. We can incorporate this learning by doing techniques into our teaching. Get students to do something. When they touch and do something and get something to work, increase their, their kind of understanding of the concept. They feel that they understand it. This is what made the difference when I went to the UK to do my MS program. And we went to the lab. And for the first time, things actually worked compared to the lab that we had to go conquer data, because we want to get A, right? We will go to the lab never worked. And then we will go back home and then write out the data and then to write a report. That is one teaching technique, learning technique that is very, very effective. We also have the problem-based learning, which you can make students to congregate around a specific problem. And then they will brainstorm ideas. How do we solve problems? In the process of thinking and brainstorming, they will talk about the principles. What we would have spent time to teach in class, the student will hash it out themselves. They figure out the principles and how do you apply that principle to solve that problem. And then we also have inquiry-based learning and cooperative learning. Cooperative learning, basically, you can make students to work in groups, and in that group, there'll be like group teaming dynamics, and then they can, students can teach themselves, pass information around. Okay. Now, let me now come back to the last part. How do we form an handshake between this scholarship and the teaching techniques within the embedded control course that we have developed? Okay, the control course that we have developed, if you are listening to the first speaker, kind of broke down the curriculum and the different aspects. If you notice, you'll see that the course that we have developed has significant hands-on components. And these components are deliberate. We deliberately did that. Now, the course has both the teaching part as well as the practice part, and they're almost 50-50. In fact, the practice part is even more than the lecture part. Therefore, in this course, most of the work will be done by students working in groups and on different projects. Therefore, significant hands-on components to facilitate learning by doing. We also have design projects. If you look at the details of the curriculum, we have suggested different labs that will be done on different scale, across the 15-week or 12-week semester that we have. Now, this design project will facilitate problem-based and design-based learning. Like the last speaker was talking about, you can make students to do DAC, digital to analog conversion, or even look at different type of control technologies, maybe PID versus MPC versus gain scheduling versus different types of technique that exist. You can make students to do projects on these different areas, and they will learn more. And then we also have the teaming and project groups that we have. Some of the project will be in groups. Like we might say, okay, for this project, we will have 4 groups, and each group will be investigating a specific problem. That maybe one group is looking at the effect of delay on the PID performance. The other group might be looking at the effect of saturation on the PID performance. The another group might be looking at why can't we do open loop? Why do we close the loop, right? Another group might be looking at stability. That in that case, each group goes around and do their work, and then they come back and present to the whole group. That the group that learns that did the saturation will come and teach the class about saturation. The group that did the PID control will come and teach the class about PID. And this is a way to get students to participate, and to involve in this active learning process, rather than you coming to class and just pouring. And studies have shown students only remember less than 10% of what you are pouring at them. It is when they get to do and use their hand, and see and taste and feel that stays longer. Okay. What about research opportunities for this course? This course allows for synthesis of idea from control theory, like the last speaker spoke about, control theory, optimization, embedded system, circuit design. This is scholarship of integration. Therefore, we can do a lot of stuff from these different fields, and also allows us to move across disciplinary boundaries. If we look at the modeling concept that the last speaker presented, a use concept of energy balance, which is a widely used stuff in chemical engineering. Also, we can also use this conservation of energy principles, KVL, Kirchhoff current law, voltage law, which is principle predominantly in electrical engineering. Therefore, control allows us to go outside our disciplinary boundaries and to encroach into other areas and put all of this together. Okay. What about the scholarship of discovery? We can do fundamental research within this course. We can get students to do a lot of stuff, including yourself and your student. You can focus either on constraint control, like our last speaker said, saturation. What is the effect of saturation? What are the techniques to ameliorate this effect of saturation on closed loop? You can develop algorithm that you want to test out on these devices. In fact, the test bed that we have procured right now, we have 2 of them. The last speaker spoke about the TC lab. I'm going to talk in a short time. I'll talk briefly about the other part. I know I'm running a little bit out of time. Okay, let me just talk about the anodyne part. The anodyne that we have got, we've got a number of them that will be distributed between Elizade and Obafemi Awolowo University. And I have a couple of them also in my lab here at the College of New Jersey. This anodyne field programmable array, but they are similar to your FPGA. But in this case, these are analog array boards, and they allow for rapid prototyping of control algorithms. Therefore, in our last speaker said prototyping of circuits. In our case, since we want to, our circuit is actually implementing control. And you can do that on a fast, analog circuit processor. For example, consider this figure that we have here. This is an implementation of a constraint control. Okay, this is a constraint control. We have some matrix vector multiplication taking place here. You have some saturation taking place here, and then you have your saturation taking place here. You can also interpret this as a neural network, if you may like to call it. This is like a dynamic or recurrent neural network, but it's implementing control. Each of these components can be implemented using basic circuits, like I've shown here. Your integration can be implemented using integrating op-amp, or you can use your saturation can be implemented using shaping amplifiers with diodes, and we can use summing amplifier to do your matrix vector multiplication. But take note, all of this requires a lot of amplifiers that needs to be powered, right? Now, we can implement this on our FPGA easily. Let me just show you. Therefore, rather than building the circuit that I've shown earlier using this component, we can prototype it on an FPGA. And what we need to do is to bring up the software and do the layout. This is a layout of the neural network circuitry that I showed before. And then when you are done with laying it out, this is similar to your PSPICE, like our last speaker spoke about. This is like your simulator. you simulate the circuit that you want to implement, you test it, you can see probes here, And this guy has oscilloscope, scope that you can scope signals at different points to show that your circuit is working. And after you have verified that the circuit is working, you download it onto the board. When this is downloaded to the board, now you have a working circuit that you can now go to embed within your controller. Therefore, we're interested in embedding this circuitry within some real-time control, which I can show you briefly here. Now, this is an example of what I've done in my lab. Here we have this anodyne boards here that have been programmed with certain, in this case, an MPC, model predictive control. It's been programmed on this board. And this board now interface with this quadruple tank system. This is a water tank system to control it. And then we have the interfaces. If you look at here, our first speaker and the second speaker spoke about signal conditioning and the interfacing circuitry. Here we have some filters to kind of interface between the anodyne boards and the system that we're going to control. And I have some amplifier here. That we have my interfacing circuitry that takes the sensor information, the sensor data, in this case, the height, the liquid height in this tank, is fed back through my filters or signal conditioning circuit into my board. And my actuation is also through some of these signal conditioning circuit to my amplifier to the system. And I have my closed loop. And the controller is programmed on the board. Now, these are some of the things we can do with the board that we have. Now, and we can test out different control techniques that can be tested on this board. Like, for example, right now in my lab, I'm doing MPC. You know, you can investigate some of the control technology that you have developed, you know, or you are currently developing your research can be given to students to implement in the lab. You know, this is how you bring your research into the lab for students to participate, you know, and in fact, your student can also be a co-author of your papers. You know, you can develop conference papers that your student will take lead and they will go present it. You know, this is a very unique opportunity for us to be able to incorporate research and our teaching to put them together and using this platform that we have right now. And we hope to expand on it so that we can start doing something, even a little way. Now, rather than investing a lot of money in procuring test beds, now we have this TC lab that is cost, very, I would say cheap, though not that cheap, but at least we have them. And this test bed can now be used to simulate or to test your control algorithm and different ideas that we have. Okay, I think I need to wrap up now so that we can use 5 minutes to take questions. Therefore, in summary, we've been able to develop this embedded control course, and it offers significant opportunity for incorporating scholarship as well as active learning techniques into teaching and to enhance student and for student mentoring. This has been, made possible through support from the Carnegie African Diaspora Fellowship Program. We cannot thank them enough, and we hope that they will continue to support us in the future. And we look forward to running this course at the host institutions and to come back and share the lesson learned in due time. Thank you very much. Let's thank Professor K. Do you want to? I think we have about 3 minutes or so.
Just a second, sir.
Yeah.
I would like to recognize the presence of Dr. Olumenga Ogidon, the HOD of Elect Elizabeth University. I would like to recognize Professor.
Thank you. Good afternoon.
Yes.
Thank you, sir. We're glad to have you, sir.
I would like to recognize the presence of Professor Shiri, HOD of Automotive, Elizabeth University.
Oh, nice to have you, sir, Prof. Thank you for being with us, sir. All right. Okay, we have just a few more minutes. Please, this is time for questions, comments, and contributions. Please, if you have any, you can use the raising of hand option, or you can just speak up as soon as you're acknowledged to do so. Let me see. Is there anybody that has made a comment? No.
Yes, I want to make a comment.
Oh, please go ahead, sir.
I want to thank you for this arrangement. And I really wish that more faculties will participate in this type of interaction. What you have done this afternoon is very good. The EU of getting students to be involved in their learning, because learning has changed. It is now student-centered all over the world. And I practice this in my teaching, and I discovered that it is very, very effective. And I learned that in Cape Peninsula University of Technology, South Africa, where I had my PhD. And I discovered that the way they lecture their students is not the way we lecture here at home. The lecture is student-centered. They give them assignments. They come and make presentations. For every course, there is a mini project in which you group them, give them real-life problem to solve before they do their exam. And I've been practicing that for the past 4 or 5 years. Sincerely, it has been very, very effective. Some students come to tell me that it was during those mini projects they understood everything we have been saying theoretically in the course, because we give them hardwares, give them real life problem, use every knowledge you have in this, you've gained in this course to solve that problem. And I won't teach you, I'll just guide you through resources online, YouTube, Google Scholar, paid publications, and they come back in 10 days and they solve that problem. So I want to say that it is a very effective method. And nowadays that we have the internet, there's nothing you are coming to say in the class that the students have not Googled. So give them the problem, guide them, make it student-centered. And when they are involved in their teaching, they will never forget throughout their life. Thank you very much.
Thank you, sir. I can also testify that that method is very effective. Although I've not learned how to do it fully, but I'm beginning to change my own ways as well to accommodate that. Thank you, sir. Anybody else? Anybody with recommendations, contributions, questions, queries, anything?
Just a second. I also like to recognize the presence of Dr. Temi Koton. He's also with the elect Elizabeth University. Dr. Kende Temi Koton is with us.
Thank you for coming, sir. We appreciate you.
Thank you. Thank you very much for coming, sir. We appreciate it.
Thank you very much.
Okay, it appears there are no further questions or comments. So it is 3:01 here.
Before you call it off, sir.
Oh, okay.
Can I do something? If you want the slides to be sent to you,
yes,
please don't forget to leave your email in the chat, and we will get back to you with the slides. We will distribute it. Thank you.
And of course, if you have things you want to say after, you can always reach out to us as well. I'm sure by the time you leave your emails, we will contact you and then you can interact. In any case, you can always reach out to any of us or to our respective departments if you can't get us specifically. In any case, the interaction should go on. We should have a big team of control engineers using ideas to solve big problems. And our nation has the need for people who can solve problems. We have a lot to solve. And I believe control can come in and do a big job of helping us with insecurity and so many other things. So
I would like to mention that Engineer Ogbede from Afewawola University has also joined us.
Oh,
yeah, so you might want to talk about that, Dr. Buba.
Yes. In the process of our interactions as a group over the last few months and the seminar and so many things that have happened, we have had people indicate interest in joining our group and helping to further enhance the capability of our team. And Dr. Ogbede from Afewawola University has joined us, and this is an indication of the fact that it is possible to expand our team as well as to form other teams as well. So, and he has made telling contributions in the curriculum development and so many other areas. So I just want to thank Dr. Ogbeide and then encourage everybody else also that this is a partnership. There's no island, there's no my university is better than yours. Everybody is together and we are all trying to make the teaching experience to be as good as possible for both the teachers and the students. So thank you, Dr. Alioke, for bringing that up. And as I said, we look forward to interacting more with everyone. Please talk to your students, talk to your professors. Let us make learning to be better. At the end of the day, the more we teach people the right things, the less we have to worry about crime and so many other problems of our society.